Hi, welcome to the ComSci 137 lecture. Sunny here. In this module, we will introduce the data link layer. Let's start. The TCP/IP protocol suite does not define any protocol in the data link layer or physical layer. These two layers are territories of networks that, when connected, make up the internet. These networks, wired or wireless, provide services to the upper three layers of the TCP/IP protocol suite. The data link layer transforms the physical layer to a link responsible for node-to-node communication. A data unit from one point in the internet needs to pass through many networks to reach another point. These LANs and WANs are connected by routers. It is customary to refer to the two end hosts and the routers as nodes, and the networks in between as links. Although two nodes are physically connected by a transmission medium such as cable or air, we need to remember that the data link layer controls how the medium is used. We can have a data link layer that uses the whole capacity of the medium. We can also have a data link layer that uses only part of the capacity of the link. In other words, we can have a point-to-point link or a broadcast link. In a point-to-point link, the link is dedicated to the two devices. In a broadcast link, the link is shared between several pairs of devices. To better understand the functionality of and the services provided by the link layer, we can divide the link layer into two sublayers: Data Link Control or DLC and Media Access Control or MAC. The Data Link Control sublayer deals with all issues common to both point-to-point and broadcast links. The Media Access Control sublayer deals only with the issues specific to broadcast links. Services offered by the data link layer are framing, flow control, error control, media access control, and link layer addressing. In a connectionless internetwork such as the internet, you cannot make a datagram reach its destination using only IP addresses. Source and destination IP address define the two ends but cannot define which links the datagram should pass. Another addressing mechanism is needed in a connectionless internetwork. The link layer address is commonly called the physical address or MAC address. Some link layer protocols define three types of addresses: unicast, multicast, and broadcast. Unicasting means one-to-one communication. A frame with a unicast address destination is destined only for one entity in the link. In Ethernet, addresses are 48 bits presented as 12 hexadecimal digits separated by colons. A unicast address has an even number in the second digit in hexadecimal. Multicasting means one-to-many communication. In Ethernet, the second digit is an odd number in hexadecimal. Broadcasting means one-to-all communication. Frame with destination broadcast address is sent to all entities in the link. In Ethernet, 48 bits are all ones that are presented as hexadecimal digits separated by colons. Whenever bit flows from one point to another, they are subject to unpredictable changes because of interference. This interference can change the shape of the signal. There are two types of errors: single bit errors, where only one bit is changed in the data unit; burst errors, or more bits have changed. Length is measured from the first corrupted bit to the last corrupted bit. The central concept in detecting or correcting errors is redundancy. To be able to detect or correct errors, we need to send some extra bits with our data. These redundant bits are added by the sender and removed by the receiver. Their presence allows the receiver to detect or correct corrupted bits. The correction of errors is more difficult than the detection. Error detection, we are only looking to see if any error has occurred. The answer is simple yes or no. We are not even interested in the number of corrupted bits. A single bit error is the same for us as a burst error. In error correction, we need to know the exact number of bits that are corrupted and, more importantly, their location in the message. The number of errors and the size of the message are important factors. There are two ways to correct errors: forward error correction where the receiver tries to guess the message by using redundant bits, and the retransmission, the receiver detects an error and asks the sender to resend the message. Coding creates a relationship between redundant bits and actual data bits. We can divide coding schemes into two broad categories: block coding and convolution coding. We will be using modulo arithmetic, specifically modulo 2, in error detection and correction. In block coding, we divide the message into blocks, each of k bits, called data words. We add r redundant bits to each block to make the length n is equal to k plus r. The n bit blocks are called code words. With k bits, we can have 2 raised to the k data words, and with n bits, we can have 2 to the n code words. The same data word is always encoded as the same code word. With this, 2 raised to the n minus 2 raised to the k code words are not used. The existence of these illegal words is the trick in error detection. An example of block coding is 4b/5b. With k is equal to 4, there are 16 data words as listed here. With n is equal to 5, there is supposed to be 32 code words. However, as you can see, some code words are unused. This means when a receiver receives a code word which is not on the list, there is an error. To detect an error, the receiver must have the list of valid code words. Also, the original code word has changed to an invalid one. An error detecting code can only detect the types of error for which it is designed. Other types of error may remain undetected. Here is another example of how the error detection works. Table A has a list of data words and code words. This can only detect single-bit errors. For example, a sender encodes 01 as 011. If the receiver gets 011, therefore it is valid. The receiver gets 111, it is invalid since there is no 111 in the list of code words. However, when the receiver gets 000, it is an undetected error because 000 is listed. As mentioned, this can only detect single-bit errors. There were 2 bits changed when it received 000. Here is an example of how forward error correction works. Table B has the list of valid data word and code word. Sender encodes 01 as 01011. However, the receiver gets 01001, which is not found on the list of code words. We assume that one bit is corrupted. If we compare the received code word with the code words on the list, the first, the third, and the fourth have a 2 bits difference. Only the second has a 1 bit difference, so it must be the second. The Hamming distance is the number of differences between the corresponding bits between two words, represented by d, x, y. The Hamming distance between the received code word and the sent code word is the number of bits that are corrupted during transmission. To get the Hamming distance, you use exclusive OR and count the number of ones in the result. For example, the Hamming distance between 000 and 011 is 2. The distance between 10101 and 11110 is 3. The minimum Hamming distance is the smallest Hamming distance between all possible pairs of the code words, represented by d sub min. From Table A, the minimum Hamming distance is 2. Table B, the minimum Hamming distance is equal to 3. Any coding scheme needs to have at least 3 parameters: code word size n, the data word size k, and the minimum Hamming distance. To guarantee detection up to S errors in all cases, the minimum Hamming distance in a block must be S plus 1. To guarantee correction up to T errors in all cases, the minimum Hamming distance in a block must be 2T plus 1. Almost all block codes used today belong to a subset of block codes called linear block codes. A linear block code is a code in which the exclusive OR of two valid code words create another valid code word. It's simple to find the minimum Hamming distance for a linear block code. The minimum Hamming distance is the number of ones in the non-zero valid code word with the smallest number of ones. For example, in table A, number of ones in the non-zero code words are 2, 2, and 2. The minimum Hamming distance is equal to 2. In table B, the number of ones in the non-zero code words are 3, 3, and 4, so the minimum Hamming distance is 3. The most familiar error detecting code is the parity check code. This code is a linear block code. In this code, a k-bit data word is changed to an n-bit code word where n is equal to k plus 1. The extra bit, called the parity bit, is selected to make the total number of ones in the code word even. Although some implementations specify an odd number of ones, we discussed the even case. The minimum Hamming distance for this category is equal to 2, which means that the code is a single-bit error detecting code. This table shows a parity check with k is equal to 4 and n is equal to 5. The code word is produced by making the number of ones even. Here shows a possible structure of an encoder and a decoder. The calculation is done in modular arithmetic. The encoder uses a generator that takes a copy of a 4-bit data word and generates a parity R sub 0. The data word bits and the parity bit create the 5-bit code word. The parity bit that is added makes the number of ones in the code word even. This is normally done by adding the 4 bits of the data word. The result is the parity bit. If the number of ones is even, the result is 0. If the number of ones is odd, the result is 1. In both cases, the total number of ones in the code word is even. The sender sends the code word, which may be corrupted during transmission. The receiver receives a 5-bit word. The checker at the receiver does the same thing as the generator in the sender, with one exception. The addition is done over all 5 bits. The result, which is called the syndrome, is just 1 bit. The syndrome is 0 when the number of ones in the received code word is even. Otherwise, it is 1. The syndrome is passed to the decision logic analyzer. If the syndrome is 0, there is no detectable error in the received code word. The data portion of the received code word is accepted as a data word. The syndrome is 1. The data portion of the received code word is discarded. The data word is not created. Cyclic codes are special linear block codes with one extra property. In a cyclic code, if a code word is cyclically shifted, the result is another code word. For example, if 10110000 is a code word and we cyclically left shift, then 0110001 is a code word. A subset of cyclic codes, the cyclic redundancy check or CRC, is used in networks such as LANs and WANs. Here is a possible design for the CRC encoder and decoder. Let's take a look at the encoder. A data word has k bits and a code word has n bits. The size of the data word is augmented by adding n minus k zeros to the right hand side. The n-bit result is fed into the generator. The generator uses a divisor of size n minus k plus 1. This is predefined and agreed upon. The divisor divides augmented data word by the divisor. The remainder is appended to the data word to create a code word. Let's see how division in a CRC encoder works. The data word to convert and send is 1001. The divisor 1011 is predefined and agreed upon. If the leftmost bit is 0, use 0000 as divisor. Actually, we discard the quotient. We add the remainder in the data word to form the code word. Let's take a look at the CRC decoder. The decoder receives a possibly corrupted code word. N bits is fed to the checker, which is a replica of the generator. The remainder produced by the checker is a syndrome of n minus k bits. If a syndrome bits are all zeros, k leftmost bits of the code word are accepted as the data word. The left figure shows the correct code word is received. Doing the same division process as the encoder, since the remainder or syndrome produced is 000, the k leftmost bits are accepted. The right figure shows a corrupted code word. The syndrome produced is 011, so the data word is discarded. CRC have good performance in detecting single bit errors, double errors, odd number of errors, and burst errors. It is easily implemented in hardware and software. Hardware implementation is fast using the XOR gates. Checksum is an error detecting technique that can be applied to a message of any length. In the internet, it is mostly used at the network and transport layer. The source, the message is first divided into m-bit units. The generator then creates an extra m-bit unit called the checksum, which is sent with the message. The destination checker creates a new checksum for the combination of the message and the sent checksum. If the new checksum is all zeros, the message is accepted. Otherwise, it is discarded. The idea of the traditional checksum is simple. Suppose the message is a list of 5 4-bit numbers that we want to send. In addition to sending these numbers, we send the sum of the numbers. For example, if the set of numbers is 7, 11, 12, 06, we send 7, 11, 12, 0, 6, 36, where 36 is the sum of the original numbers. The receiver adds the 5 numbers and compares the result with the sum. The two are the same. The receiver assumes no error, accepts the 5 numbers, and discards the sum. Otherwise, there is an error somewhere and the message is not accepted. If we send the negative of the sum, which is negative 36, the receiver simply adds everything and a result of 0 is expected. However, in the previous example, the checksum negative 36 cannot be written as a 4-bit word. We can use the ones complement arithmetic. This arithmetic, we can represent unsigned numbers between 0 to 2n minus 1 using only n bits. If the number has more than n bits, the extra leftmost bits are added to the n rightmost bits. For example, 36 using 4 bits is 6. Negative number can be represented by inverting all bits. Here is the computation of the checksum. Traditionally, the internet has been using the 16-bit checksum. The sender or the receiver uses 5 steps. For the sender, the first step is the message is divided into 16-bit words. Then, the value of the checksum is initially set to 0. All words, including the checksum, are added using 1's complement addition. Then the sum is complemented and becomes the checksum. The checksum is sent with the data. At the receiver side, first, the message and the checksum are received. Then the message is divided into 16-bit words. Then all words are added using 1's complement addition. Then the sum is complemented and becomes the new checksum. The value of the checksum is 0. The message is accepted. Otherwise, it is rejected. This ends Module 12. Thank you.